Welcome, and thank you for inviting me back. This is the second time we've presented at this venue. This is the very first time that we have attempted to do a live demo. Please be patient. Like any other live demo, there's always something, and we've done our best to avoid issues, but there's always one possibility or another. The demo is actually about software, the tools that we use, the tools that we created to be able to build CPUs, both the software that they use and the CPU itself. Consequently, it's about specification because that's how it's done. How many have seen our videos online? Okay. There'll be some assumptions about how the rest of the mill actually works, but feel free to ask questions if something appears to be totally in Greek. It is a general purpose CPU family with a substantial advantage for a number of reasons, both power and performance over conventional architectures. There hasn't really been much new in conventional architecture since the introduction of caches 30 years ago, or caches in broad machines. The caches actually are 50 years old. And it had a design goal that it would run general purpose code straight off the web without rewrite. With all of these advantages. This particular talk talks about the architectural strategy that we use where the architecture is configurable. It's built out of a set of specifications rather than a million monkeys sitting up there writing Verilog, which is the more traditional way that hardware is done. In order to make that work, we've devised a mechanism we call attributed specification, and I'll be explaining that. That is used to define the operation set. Nobody picked out the bit this means this, and bit this means this, and bit this means this. That's all done mechanically by our tools. And the configuration for individual products is done by composing components at board, chip, and core levels. Also, as you'll see, and from those configurations, we build a set of tools that will eventually be available to our customers when we actually get this to have something that you can put on a real board with real customers. There's been a series of these talks. You can find the rest of them on our website, both the slides used and the videos. The videos for this will also be going up at a certain point after post-production. We had wanted to be able to have two projectors happening simultaneously, one showing the slides and the other showing the compiles and what have you actually going by, because it is a live demo. Unfortunately, as you see, there's only one projector there, and so that isn't working quite right. We hope that in post-production we'll be able to make it look like there was actually two inputs side by side, but you folks are going to have to bear with switching back and forth between the slides and the compiles. Indeed. As always, I have to mention that these talks are intended to provide an intuitive understanding. I'm more than happy to go into the details, but it's intended to be at a level appropriate for a non-specialist. And what actually goes on underneath, as I hinted before we started, is distinctly more complicated. The basic story is specification. Unlike other talks in this series, this talk does not talk about the architecture itself. Instead, it describes how the operation set and the individual family members, the mill is a family in the sense that the System 360 was a family of compatible machines, how the family architectures are specified. It will describe and demonstrate some of the software tools. Because of the peculiarities of the machine, some of those tools are not quite familiar to you, I suspect, but by the end of the talk, you should find them more comfortable. You can't build the hardware entirely out of specifications. There are, in fact, still manual steps, which our hardware team has to do for place and route and other things, but essentially all the software is built mechanically, and large quantities of the hardware up to the point of final tuning and layout and determining of crosstalk and those kind of mysterious things. Note that I am a software guy. Those kinds of mysterious arm wavings that the hardware people have to go through. The specification tools I'm describing are used internally by us and have for several years now. They are not intended to be a commercial product in their own right. By using the tools, we're able to create new CPUs more quickly and at lower cost than usual. The goal here is to be able to target niche markets very fast, and the tools are essential. The traditional mechanism followed by a ordinary large vendor is simply not economically practical for a startup. The intended audience of this talk are tool designers, software developers, and so forth. Those of you who are interested in tool development and tool use. Specification. As I said, it's a family of CPUs. What defines the family is an abstract mill. It is a sort of the union of all possible mills. That abstract mill can be used to produce individual family members, and that set of 4 that you see there are, in fact, proof of principle configurations that we, in fact, use internally to make sure that everything is working right across the range of possibilities that we intend to target. Tin is, as you might expect, the smallest possible mill, the smallest possible commercial mill, and gold is right up there at the high end. There's potentially, if we could go further than that, we think, but we won't know until we get further along in the actual manufacturing process. The members differ in concrete operation set. Tin, for example, has no floating point in it at all. It just does not have these units, and there are customers for whom they don't care about floating point. There's a lot of embedded stuff that is happy doing nothing but integer. And so there's no point that they should have to pay to have a floating point unit on a chip they're not going to use it. So they differ, and they differ both in the operation set and in the microarchitecture. You create a concrete family member by writing a specification. You'll see that. In fact, we're going to do one. Now, from the specification, which gives you a tin or a copper or whatever, our tools mechanically generate system software such as compilers, assemblers, debuggers, the simulator itself, verification tests mechanically produced, custom for the individual capabilities of the machine, internal and eventually external documentation, and the hardware framework that the hardware guys use to glue other stuff around and fold and turn into gates. Representative tools. Where the transition from the abstract to the concrete family members was by specification. The transition from the family member to the individual tools is data-driven based on the contents of the specification. Now, short digression. In order to explain and show you what the code is doing, I have to show you some code. And at this level, we're not talking C, Fortran, COBOL, or whatever your friendly local language is. We are talking assembly language. And the mill is distinct and novel enough that its assembly language is not, even for those of you who are familiar with regular assemblers, it's not quite what you've seen before. In particular, the mill is a wide issue machine, and a single instruction can contain multiple operations issued together, and it is an exposed pipeline machine, which means that everything goes lockstep through the pipelines, and while everything that issues together, they do not necessarily retire together. The software has to be prepared to deal with this fact. The assembler syntax is in fact C++, suitably disguised, you'll see. Traditional assemblers have two passes. We're not talking about the things which are behind GCC, but a more traditional two-pass assembler. The first pass is written in what amounts to a meta-language, which has an extraordinarily powerful set of facilities to create data structures, to create new code on the fly. The first passes are typically a macro language, and a good macro language you can brush your teeth with. They're wonderful things, and they will also give you more than enough rope to hang yourself with. The function of that first pass is to create a second program, which is written in machine language. Now, if you don't do any of the bells and whistles in the first pass, you can write directly in machine language, and the first pass is a no-op. But usually you don't do that. Usually you make use of the facilities that the first pass offers. So from your source file, written in macro language, the first pass will give you another program which is semantically the same, but now in machine language with the individual ops of the hardware. That second pass then translates the machine language program into bits in the load module. This is a classic two-phase assembler. The Milcom assembler uses a C++ compiler. The first pass is, in fact, the C++ compiler. We use both GCC and LLVM. It does not matter. And you could use your own C++, whatever you prefer. It translates programs written in assembly language into an executable, because the assembly language is, in fact, has the syntax of C++, and you can compile it, and the compile will produce an executable. So the source file, written in C++, goes to the C++ compiler to produce an executable program. And the second pass is the execution of that program. When that program runs, it emits the binary, puts the bits in the executable file, and away you go. Now, this is a bit boggling for many people who've not seen this trick. We did not invent this trick. I first encountered this trick in the late 1960s, being used for a front-end machine. In that case, the compiler was not C++, the compiler was Algol 60, but the trick was the same. So each assembler operation written in your source code is a C++ function call. So if I have in a conventional assembler, add two numbers, B3 and B5 are numbers off the belt. Those of you who have seen the videos about the belt know what that means. You can think of them as being pulled from a register file. The exact same semantics in milassembler is a function call where the function name is add, and the arguments are coming in as parameters. A jump, where a conventional assembler will automatically recognize and create a new identifier. C++ has these rules about declaring things. So instead, we actually have to express our label targets, not having them implicitly created by your assembler, but instead we pass them in as strings, and the tool keeps track of them. And then similarly, if you want to plant a label, you have to do the same thing with the string. But nonetheless, there's a direct one-to-one mapping here. The syntax changes, but it's an assembly language. A mil instruction is a C++ statement. Remember I said that instructions can have more than one operation in them. So that's a statement. The whole thing is a mil instruction. The semicolon tells you the end of a C++ statement, and that all of the operations in that statement correspond to one mil instruction. the individual operations are separated by commas. How many of you ever have overloaded the comma operator in C++? Hands up.
Wow, one person.
Okay, well, it's not, it can be done. Bjarne was asked one time, why on earth did you ever permit a comma to be overloaded? And the answer was, well, it looked like it'd be fun. If you know Bjarne, you'll know that is very characteristic of it. Because we're using the compiler as a front end, you can use C++ as a meta language. So all that matters is how many times do you call one of these operations, because every time you call one of those functions, that binary goes spit out in the output file. So if I have this sort of code, where I've got a loop, which is repeatedly calling one of our assembly language instructions, guess what? That's going to give you the same machine code as that. So you actually are doing metaprogramming, not in a macro language, but in C++, because that is our front end. We do make use of that, especially when we're having to mechanically generate things like verification tests, where there's just bazillion things where you want to run the changes of something, and you just write what it wants to be, and bang, 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 and the assembler produces them for you. You can make your own program. Equivalently, you don't have to do that at all, and we, in fact, none of the examples you'll see tonight actually make use of that facility at all, because I want to be able to show how things actually operate at the machine level. So although the C++ compiler is going to eat it, it's not going to have anything to have except a straight one after another function call. So we need a test case. And in an effort to make the test case simple, we've hypothesized that there is a customer who has a market somewhere in the embedded space, and he needs very, very little programming compute capability. As little as possible, because is in no sense is he compute bound. But he does need a limited amount of floating point capability, and he needs one special operation. So imagine that you are this customer, and I'll show you what the mill can do for you. The test case, and in an effort to keep fat finger typos out of the demonstration and presentation as much as possible, a large amount of this code for the test case has been pre-written, but we'll be changing it on the fly as we go along. This test case contains this small code fragment. Con there is a machine operation called con, meaning constant, and its job is to take a literal constant and drop it on the belt. The W there says that this is a 4-byte operation, that the constant we are to produce is a 4-byte constant. You can have a 1-byte constant or an 8-byte constant or whatever. This large mass of junk there deals with the fact that the C++ compiler is running on a non-mill host, but it has to generate code for a mill. Who has done cross-platform builds? Okay, I don't have to say any more. You'll know what you got to do about it, and this is what we do. We're calling into a math library which emulates mill mathematics, because what GCC would give us 80-bit floating point or some obscure thing, which in fact we don't want. So what we're actually calling in there is part of our math package, so that we get the right constants. Add B is a floating point, binary floating point. We also support decimal floating point. A binary floating point add. It's adding the result of the two constants. And That is the two constants being picked up, B0 and B1, the two most recent values on the belt, which were, of course, dropped by the two cons. And then there's a group of no-ops whose job it is to idle along until the floating point unit is done, because, as I said, everything runs in lockstep, and we're not doing out-of-order operations. So for purposes of illustration, you're going to see no-ops in there. In actual practice in real code, there'd be something else useful being put in those places instead. However, tin, which is our smallest machine, doesn't have floating point. So let me show you what actually happens when we attempt to do this. We are here, and what we're actually doing is we're attempting to build our test case, which already exists. You note the con, and the add b. Well, here's a diagnostic coming from the assembler saying there is, in fact, no operation add b in the slot 0 where we have placed it. This member doesn't have one, and the assembler knows that and tells you. Otherwise, the code is as you've seen before.
Does that mean there's no integer add either?
Again?
No integer add?
Oh, there is certainly is an integer add. That's a floating point add.
It has a different form if it's integer?
Yes.
Thank you.
You'll see. Okay. Add B is add binary. Add D David is decimal. Add D David wouldn't work either. It doesn't have a decimal floating point either. Okay, so let me come back to the slides. And we've done that. So we're going to build a new member, a new family member, whose name is surprise demo, and it will be identical to tin, except that it'll have a floating point unit that tin does not have, and we're going to add an operation later. So the first step will be, oh, you're able to do that, okay.
Yeah.
I didn't know that you could do that. Okay, so we will go down and copy the entire build tree for tin over into a new tree called demo.
Okay.
We'll now go into it. Now we have to tell the build tool, I think that's next. And we have to tell the build tool that this thing is now called demo rather than tin, so all instances of tin appearing in this will wind up being changed to being called demo. This is the usual .rc file that our internal build tool uses. Ignore all of the information except the fact that we do have to tell it what is the target member. Okay, we can come back out of that. And I think the next step is a make deep.
Clean deep, yeah.
Clean deep, right? The copied over tree contains all of the results of compiling for tin, and we don't want to use those libraries or anything, so we're going to throw all of that stuff away, leaving us only with the sources. And
Okay, so I should.
okay, now we're going to go over to the directory which holds a specification for all the different family members. And we are going to have a copy over the specification for tin to create a specification for our new family members. And we're going to have to edit that slightly because that file the new file contains some references to tin that we have to fix. And every instance of tin should be replaced by demo in that. There's two of them. They're up at the top. You are looking at a real specification file. That's a real one. And tin appears twice. And lastly, down at the bottom, there where we're specifying what functional units there are in the individual slots. There's only one pipeline on a tin, and see there's an ALU functional unit and various other functional units. It's got a multiplier, but we're going to add a floating point unit.
Is integer multiply part of the specification then?
Yeah, well, that's it. If we didn't have a multiplier, we'd take that out, and there wouldn't be a multiplier. That's that simple. BFP is binary floating point functional unit, as you might guess. And save. Now, if we were to go back to where the place where the test case was and build ourselves a new thing based on the specification, it would work, and we would have a family member that does floating point, which was otherwise identical to tin. However, it takes a little while to build a new family member, and we also want to do something else. So I'm going to combine two sets of changes into one build just to speed processes up. So the next step is, we're still in the process of making this be good for demo. This is our original test case. You'll recognize there's our floating point expression, and the assembler says what family member it wants. It said this is code for 10, and we have to change it so it says it's a code for a demo. Okay. And now I think we're out, and now we could have it built, but we're not going to. I think at this point we're now going down to memspec. Yes. So we copied the code tree to make demo. We cleared the old files out of the tree. We told the builder tool to use the new member rather than the old member. We created a new specification by modifying the specification for tin. We populated the pipeline slot with floating point. And now we're ready to define a new operation. Now, because any operation we're working under sim, and any operation we define, we're going to have to write the code in the sim that knows what that operation is. We want to make it fairly simple. So we have pre-picked a sample operation, but I will let you make some modifications to it. An operation is defined by a composition of attributes, and they are comprised of a core operation plus values for a bunch of different attributes. So if that is one of our operations, and that is in fact an operation, the core operation there is add. You've already seen add B. Well, this is add US, but the core operation is add. A couple to that are attributes. One of those attributes is the domain. What computational family does this belong to? That's defined in this case by the U, which says this is an add in the unsigned integer arithmetic domain, just like B says this is an add in the floating point binary domain. In addition, the mill cares a great deal about overflow. Most machines let you hang yourself, but the mill lets you control the overflow behavior of operations. So one of the possibilities is indicated by the S there that says in the event of an overflow, we will use saturated arithmetic and will return the largest possible value. Okay? Many embedded machines have saturated arithmetic in hardware. We do too, but it's much less common in general purpose machines. Instead, you are permitted to hang yourself. The other attributes not coming off of the mnemonic, for example, the first argument, whose attribute name is opand0, says I take the value from the thirds, indexing from 0, belt position. And similarly, m0 says the value 17 there is a literal. So this is a add immediate unsigned using saturating arithmetic, and that's how you specified it. Now, some specific values are supplied by the mnemonic, some by the arguments. There are roughly 50 attributes, but only a few of those are meaningful for any given operation. The attribute values, most of them are enumerations. For example, there's one of the attributes. Guess what it's used for? Shift operations and a few others. Contents code. That's used for conditional and unconditional branches. The value there says, is it branch on true, branch on false, or branch on conditional? The attribute tells you. The core operation is merely branch. There's our overflow code. There are, in fact, 4 possible overflow behaviors. Raise a hardware complaint, ignore it as is commonly done, saturate, and produce a double with result which cannot overflow. Those are your 4 possible behaviors. The domain, which you've also seen, well, those are all the different kinds of things that an ad might be into, although not necessarily all of do you have all possible domains for all possible operations. They can be specified individually or as bit sets as a convenience for notation. The mnemonics themselves, each attribute and the core opcode has a text string affiliated with it called its nick, short for nickname. Thus, the attribute value leftward has a nick of L. Rightward, naturally enough, is R. Signed is naturally S. Unsigned, naturally U. So what the software does is it concatenates all these nicks in order to create the mnemonic of the final machine operation. So that one, for example, well, the operation is shift, rightward, signed. Not only does the tool regular and easy to support and add things, the entire instruction set in the mnemonic system is regular and easy for you to keep in your mind. If you know what the behavior you want, you can make your own assembly language mnemonic and without having to look it up in the book. And some of them do get rather baroque. Ours is substantially more regular. There are roughly 120 core ops, and all the combinations of the core ops and the attributes are a little over 1,000 different mnemonics. Besides its basic type, the specification for each attribute tells you how the values wind up being expressed in assembly code. Perhaps it's based on coming from the mnemonic. Perhaps it's coming from an explicit argument. In some cases, it can be derived from combinations of other attributes. You don't have to specify at all. It's figured out and then included in the final information. We have to say how it is that they're encoded. Does it have a unique bit field, and is that bit field arranged so that it can be decoded early or late in the decoded process? Hardware cares. Or are all the attribute values merged into a sort of super opcode field? And there's also attributes that are entirely internal and never wind up being encoded at all. And how the set of permitted values are determined. Things like leftward and rightward, well, they will be the same for every possible member. You don't have some members that sort of shift upward. That doesn't exist. So left and right are the only things that are meaningful. However, on some values, for example, the bit number, different mill members have got different bit widths, and so the attribute value range for a bit number differs for different family members. But for any given family member, all operations that take a bit number have got the same value range for a bit number. On the other hand, some things do not even have that degree of consistency. After we've allocated all of the basic operations and their cross product of their attributes, there's entropy left over. Typically, on the average, half a bit worth of entropy that is left over, and many people on many machines put an immense amount of time trying to squeeze the last bit out of the opcodes. We don't. We just simply take all the leftover entropy and put it into dynamic constants, things like add immediate, so that the range of values for an add immediate will vary from machine to machine and even slot to slot in the machine because the immediate range is set so as to soak up all the residual entropy of after we've made use of everything we do have to schedule. So we need a candidate operation. It will use attributes. And there is our candidate operation. We'll assume that what we have got two half words, that we want to shift one of them by a certain amount, add the second one, and add one. This is the kind of bit packing that is typical on the data plane of a router, figuring hop counts and so forth. And in many cases, performance on these things is critical. And the naive assembly language for that, of course, would be first a shift operation, an add operation, and an increment operation. However, a physical ALU can do all of that in one cycle. The shift part is merely a matter of which wires get hooked to where. The add is an add, and the +1 is merely a matter of setting the carry bit on the low end. So that all of that, if you only had the operation, would be one cycle, not three. And we're hypothesizing that our customer cares and wants this to be added. So we need an operation. This is going to be our operation. We need a name for this operation. Let me see, likely. The lady in the back with the striped shirt, do you own a cat?
I do.
What's the cat's name?
Pepper.
Pepper. What a great name for an operation. Your Pepper is going to go down in just like a certain possibly there and possibly not there cat used to be. So this Pepper will now be an operation. We also need to pick a value for the shift count. Obviously, this is going to be determined by the external field size, but I need to pick a number. Gentleman here in front, would you pick a number somewhere around the middle of a 16-bit operand?
An integer, right?
Yeah. An integer.
7.
What?
He said an integer, right?
Yes, a small constant, which will be used as a shift count.
Okay, 7.
Oh, that's going to be too easy because the pre-code is already set up to be 7. We can leave it being 7.
You're right. That must be where I got it from.
Most likely.
11.
Okay, that's not going to leave us much room, but will any of our tests always overflow with that? Yeah, I need it smaller.
3.
And better off larger, somewhere between 5 and 9, but not 7.
This is like the magician who
Yeah.
wants me to pick the cards.
Yes, my apologies, but the code won't work right if we push it too far one side or the other side. 5 it is. Okay, so we have a value for n and a value for a cat. So we're now going to switch back and define a new opcode. This is the main, the core operation, like an add or a multiply is the core operation. Pepper is now a core operation. We'll be adding attributes to Pepper. I hope Pepper is not a Manx cat because I don't have any tails to add.
Why would an 11 give you problems?
Hmm?
Why would an n of 11 give you a problem?
Because all of the sample test cases I have uses a left-hand value which shifted over 11 would have been off the end of a half word.
Could I specify a full word in this construction?
Yes, but we already had the code written
Fine,
and
okay.
would prefer not to. Those afterwards, I'd be more than happy to change it and give you your whole word and give you your 11 and everything. Having it pre-written is to lower the chance of fat fingering the typing the code in. Are we up?
Yeah, don't walk around.
Yes, boss. I tend to pace. You'll see here that we have an enumeration, and that enumeration is in fact all of the core operations. There's the add op and any op, and these are some decimal ops. There's a divide, equal, so forth. These are all the core operations, and there's 50 of them or something like that. And we've pre-written one in here, which we're now going to change to be from being new op to being pepper. So that's now sitting in the enumeration. And now it's an unfortunate fact that C++ is not very good for introspection, reflection. And one of the things I find most annoying about it is that you can't get the print name of an enumeration. Real pain in the butt. So instead, we wind up having an array of strings which contains the print name of all of our enumerations, and we have to put the print name in. And you'd think the committee, after all these years, the problem is, of course, is that there's this legacy sense that enumerations are really defined, spelled differently, and no matter. I get on the hobby horse of the subject, but in any case, when we add to the enumeration, we have to add to the print name arrays.
Ivan, this is off topic, but there is something called the X macro. Please Google for it. It brings some solution to that problem. The X macro.
This code and this approach is 10 years old, and I doubt it existed then. But whenever something like that actually comes into the standard, or even into Boost, we would probably convert it. But we're too busy writing new code to worry about going and modifying old. Okay, now, along with each one of these enumeration, there comes some traits, and this is the attribute traits for our new pepper op. One of these is what is going to be the mnemonic when you write it in assembly language. This is not the print name. This is of the enumeration, but the core mnemonic, which will be there. And there's a little bit of a documentation string, which winds up being incorporated when we are doing documentation, mechanically generated documentation of the operation set. So it's called scaled addition. And the pepper op here tells us what is the enumeration that this information is being attached to. And as you see, there's similar ones of these for all of the other ones. Each one carries the assembly language mnemonic and carries a brief documentation string. So we have to add to that, and we're done. Now we have to add a specification. What we did before was groundwork, so as to give us something we can write in our specification. Op visibles is the set of operations which are going to wind up being visible to the assembler. There's also other operations which are internal use only, but that's what this is. And this long thing here, is an example of a specification for one operation family. It tells you It's obviously a constructor for something called op pattern. It tells you which of the 6 blocks that the mill encodes operations in will this be in. This one's in XU block, and in fact, all of these are in XU block. What is the name of the core operation? And the rest of the information are attributes. This particular one says, we may wind up changing this, but this particular one says we are going to support both signed and unsigned integers, that we will support all possible overflow behaviors, all 4 of them, and that we're going to support both scalar and vector forms. And it's dyadic. It takes two arguments off the XU belt. That's a specification for an op. We're offering a second one, which is a notational convenience, doesn't actually add anything, but for if you are using the default ignore overflow, and consequently the behavior of signed and unsigned is identical, the second specification tells the assembler that that's perfectly okay, and the assembler will recognize something that doesn't specify overflow or domain, and it will use this one, and the assembler will turn that into the corresponding the fully specified one. So the second form here is a notational convenience. The first form here is the real specification. We'll get back to more of the meaning of those patterns later on. Now, besides specifying our operation, we have to say what it means. And because we're not actually going to be putting these things into a fab and put onto a nice big silicon platter right here in the presence of this meeting, we're going to be doing it in simulation. So we have to tell the simulator, what does this operation mean? And we actually have done, pre-written. NN here is the number which needs to be changed to 5. Okay, that's the shift count, and it gets used by each of these. Each one of these functions handles one of the operations. So there's about 1,000 of these functions scattered over several files. The name of the function is the concatenation of the mnemonic and the signature. The signature being XU, 2 values off the belt. Other ones will be different. You need to not do that manually or just globally change new op to pepper.
Oh, okay.
Because there's 8 of them, signed and unsigned, and all 4 rounding modes. And if you look, you'll see now we have pepper, pepper S, pepper U, and so forth going down. The arguments coming in here are after the sim has taken all the arguments apart, because this is just supplying the semantics, and the value of what it does. This 2uint and 2uint over there is converting values into the target arithmetic form, because again the sim has to use target arithmetic, not host arithmetic. But other than that, well, it's a shift followed by an add followed by another add. Hey, guess what? That's what we had, right? So there, that one line is telling the simulator, what does this operation mean? Questions? Clear? I mean, I'm not expecting you to understand what the code is, but to get a sense of how you say it. Yes?
What's the return value? False. It seems to be false everywhere. Return value is false everywhere. What does that mean?
The return value is not false everywhere. The return value tells us whether the semantic routine detected a semantic error. In this case, there's no semantic errors that the sim is checking. It'll take any bit pattern, but for other operations, it is meaningful, and then the stuff that's calling this does appropriate things. Any other questions before we leave this? Okay. Yes.
If this were saturating, where would that be specified here?
If this were?
If this were saturating, you have pepper S, but that's signed.
That's
not
signed.
saturating.
Can you scroll up and find SS? There should be a pepper S. Oh, excuse me. No, I stand corrected. There is no pepper SS. The saturating is already coming in here. The overflow code, that argument there will be saying saturating. If it says saturating, is overflow code tells says what is the overflow behavior, and that in turn is being passed into the shift and the add so as to obtain the correct overflow behavior. So the individual shift and add operations in the math package that emulates the target math also are themselves aware of overflow behavior, and they're taking in the desired behavior as an argument. And what they produce and what will ultimately wind up in this R, which is the result, will depend on whether they in fact detected the fact of an overflow or not.
Well, then how does a programmer specify either saturating or some other overflow process?
When you write it in the assembly language.
That means a separate mnemonic. Where does it show up here?
Doesn't.
Because we haven't defined it here?
No, it has been defined. The tools know about overflow behavior, effectively remove that out of the mnemonic, only have to have the cases which do not handle that and treat overflow as an argument rather than as a different function call.
I think he's asking, why didn't you define any of these ops that will take an extra letter on the opcode to ask for saturating? Because it's not meaningful in this case? Or?
No, because the cross product of all of these winds up being huge. So two of the most widely used attributes got stripped out so that we would not have just too many functions. The two that are stripped out is, you really don't want to light up, do you? The two that are stripped out is overflow behavior and rounding mode and floating point. See, there's 6 different rounding modes, and if we didn't strip it out, every one of the floating point operations would have 6 functions instead of 1 function.
So you only have to write this many, but the code then spawns it out to the whole thing.
No, it doesn't mechanically produce that many functions. It converts the attribute into an argument rather than using it to derive a function to call. Yes?
This might be too low level, but R is the result.
R is the result.
It's being passed in by value, not by reference.
It's a complex object.
Meaning?
Scale in to type that might be for a reference.
It's a struct, you mean? It's a struct? It's a struct? Is that what you mean?
It's a class.
It's a class.
Scalens are classes too. Well, there are all scalens there.
So I think I know what the confusion is here. This is just the code that executes it in the sim.
Yes, this is just code in the sim.
So
This is supplying the semantic meaning of our new operation. Okay.
right, so you don't need an exploded copy of every one of these.
Well,
No.
then is there a third argument besides the 2 belt arguments to indicate how you want overflow handled?
The belt arguments are happening at runtime.
Yeah.
This is at definition time. This is saying, what is the semantics?
Okay, then I'm still puzzled how the programmer says I want saturating arithmetic on this instruction.
But this isn't an instruction. This is a simulator which will implement the behavior when you write such an operation.
The programmer will say something like pepper SS parens B3, B5.
Yeah.
That pepper SS is a function which I assume will get code generated at some point here that we haven't seen. We'll get into that?
You'll see.
Okay.
Can we get back out of this? I'm happy to come back and go into it in greater depth.
Okay.
And now we're going to start to build our new family member, incorporating the floating point and with our new operation.
Okay. Oh. Okay. There.
Okay. And this will proceed to chug for some time. So we added a new opcode in adder.hh. We added its print name. We defined a few traits. The argument signatures you've already seen. I wanted to get the compile started because they take a while. Some of the values come with attributes coming from arguments rather than from the mnemonic. So the different argument kinds determine what the attribute will be that gets set. If it's an XUarg, then that means that this attribute will, this is a value for an attribute which indicates a belt position. An imarg, naturally enough, is a small immediate constant. A bitarg is a bit number. An offarg is a load store offset, which in the mill is a 32-bit offset. The argument nicks wind up being concatenated signatures. So if the signature is XU bit sig, this means that the operation is going to take a belt position and a bit number. A typical use of such a thing is the set, reset, test, and flip bit operations, which say a belt position to say what value are we testing a bit in, and a bit number to test. So this is a typical signature for that category of operations. This big thing is typical of a load and store operation. It's an address space, an offset, and a width. XU sig, surprise, 3 belt numbers. The operation set is uniquely defined by the combination of the mnemonics and the argument signatures. The operations are defined as patterns. You saw one. It comprises the core operation and its encoding block, the argument list, and meaningful values for the semantics. The software determines the cross product of all of the possible combinations of attributes and generates a unique operation for each member of that cross product. Thus, this particular example says it will be encoded in the XU block, just like our pepper operation is, that its core operation is an add, not a pepper, and in this case that it has to be supported for both kinds of floats, which is both binary and decimal, supports all 6 possible flavors of rounding, and it takes an XUarg, which means that it takes 2 belt operations, 2 belt operands. That defines 12 different operations, we call them models, 6 different rounding modes for each of the 2 different floating point domains. As a result of the compactness of this, that opspecs.cc that you saw that we made that change in, that's only about 3 or 4 pages of code. And that defines the full 1,000-odd instruction set. There are around 1,000 different models. Now, we could decide what it was that we wanted for our new operation. Rather than restrict ourselves, I let it have all possible combination of the 2 attributes of interest, but we didn't have to do it that way. For example, we have to specify a domain, but should it be signed in? Should it be unsigned in? Should it be something else? There's nothing that says it has to be both signed and unsigned supported. It may be only one or the other, and you would then have written it differently to say I want only the unsigned in domain, not both of them, but whatever. The overflow possibilities, it can be ignored, marks the result as an error. Saturate, produce a double width result. Pepper is going to have all four, but we could have picked any. And if the ones which we omitted in the specification, remember that floating point error we got in the assembler? If we tried to use one of the ones that were omitted in the specification, we would have gotten the same error. This machine does not support this operation in this lot. Where to encode it? Well, in this case, we've got less of a choice. The adders are all reached from XU blocks, so if it's going to be using an adder, and this operation is going to be using an adder, about the only possible choice is it has to go in XU block. And again, by its semantics, it's going to take in two arguments, so we don't really have much choice except XU arg, XU arg. We added the specification. We added the sim implementation. We are in the process of building the sim. Yes?
Do you do any optimization on all the ops you create unique or one substitute can?
There's some very interesting code in there. The bin packing problem, that is to lay out all possible combinations in the most dense way, is NP complete, NP hard, NP something. So, in fact, the numbers are small enough that we actually do use an internal exponential algorithm because it's going to be replicated across millions of chips. And this is why it takes 20 minutes to build a new member, because it is in fact doing the NP complete perfectly dense encoding as it figures out which bits mean what. Perfectly packed.
How do you deal with stability issues then? Because imagine, like, you go into production, you produce a chip, then you want to, like, rebuild the tools. So if you're using these algorithms and if there's any heuristics, then you could be incompatible.
The tools are built as part of the process. You're watching it. You'll see a new assembler and a new sim being built right now. That's what's happening right now.
Or should you build new tools for an existing chip if you need to tweak stuff, or is that a nonsensical question? Because
well, we don't have existing chips yet. Won't for a couple of years even.
And part of the tools is also, you mentioned HWJet, which I assume outputs like Verilog or something.
What winds up being produced for the hardware guys is a set of C++ Verilog drivers that are themselves compiled, and when that program runs, it spits out source Verilog. This tool doesn't produce Verilog. That requires too much Verilog knowledge, and we don't want to put it all in. Instead, this produces drivers that go through yet another tool chain that ultimately produce Verilog. And then there's manual steps after that, as I said. The software side is all mechanically done, but the hardware side does require manual steps.
In a sense, the tools are once used. They are once used. Any chip that you do with that tool is just for that chip. The next chip has new sets of tools in a sense.
I'm not getting that.
The tools are one use.
They're
In other words,
unique.
it's one set of tools per member. Once you've defined the tools for a member, that you don't have to define another set?
What actually winds up happening is that the tools are one use for certain tools, and they are multi-use for other tools. The way the sim works, if you've ever written a machine sim, by far the most time-consuming process inside a sim is not the simulation, it's decode. It is figuring out what these bit means and then branching out into the thing that simulates it. So we actually, our sim, the simulator generation process is on a per program basis. So we generate a unique simulator for each program that is being produced. And that generated simulator already has the decode done. So instead of executing and decoding operations, we can find the operations. If you're running something like a JIT, we can in fact go and do the decode. But instead of stepping through a pointer through memory and pulling up the bits and decoding the bits and then doing it, we step through a sequence of function calls which are what those bits mean. This completely removes the decode step phase out of the sim and increases somewhere between a factor of 8 and 12 the speed of the simulation. If you've ever worked on the inside of a machine simulation, you know that decode is expensive, and especially for something like the mill with the complex decode. So certain tools, you do it once, you never do it again. You'll see an example later when we're generating our MMIO tables, the MMIO map, which is done once. That's essentially permanent unless you make a change to the foundry member and make a new, then you need a new one. But it doesn't depend on the program that you're going to run on it. The sims, on the other hand, do depend on the member that the program that you're going to run on that foundry member, and that's purely an optimization for performance overhead. One thing that CPU development does is it goes through simulation cycles at a simply phenomenal rate. And it winds up in the development process. Simulation does in fact wind up being a time-critical performance overhead to boot up Linux. In sim, you're looking at a week's worth of execution. And then you change one line in the code and you got to do it again. Simulation speed matters, and so we've organized our sim to work in this way.
75,000 times. 75,000 times slower than the chip.
Much slower than the chip, and we will look forward to the day in which we can do simulation on an FPGA as opposed to on software, which will give us that much more of a speed gain. But we're not yet at the FPGA level, although we're hard at work on it. Yes.
So now you're generating the bin packing for the hardware level instruction set. So what about the representation of the portable object code?
Okay. Tin has got no floating point. What do you do if you want to do a floating point operation and at the member independent compiler, where C doesn't know anything about what the machine is going to run on? The way our tool chain works when you're running off compiled code is that the result of compilation specifies for the abstract mill, which contains everything. And at install time, or possibly at load time, or possibly as a freestanding program, we run a program called the specializer that takes the representation in the abstract form and produces a specialized form for the particular target you're going to run on. One of the first things that the code coming out of the compiler knows it's running on a mill. It's got mill operations in the intermediate code stream. But one of the first things that the specializer does, as it's loading in the representation of the program, it looks at the operation and says, "Oh, you're a model it doesn't exist for me," and it will replace that node in the program graph with this hunk of other stuff in a different graph and just plug it in. This is emulation substitution. For floating point is probably what that emulation substitution is going to turn into a function call running off to a library. But what the emulation does is part of doing the specializer for a particular target. And it can be anything. You can substitute anything you want. There are certain operations. The machine is not going to work if you don't have those operations in place. like call, for example, and branch. Possibly add even as necessary. It's not clear, but large hunks of the operation set do not actually have to be present. In particular, obviously, the floating points.
But when you insert a new instruction, you have to run two bin packings, one for the hardware level and one for the memory independent level.
I'm not getting that.
One for the hardware level and one for the memory independent level.
There's no bin packing for
Two
that.
bin packings.
The member independent form is not in binary form. It's represented as graph structures. Who's been inside the back end, the middle end of a compiler and knows what a compiler instruction, an intermediate code looks like? That's what that form is. It's a linearized form of intermediate code.
It's done.
Well, but don't think we're done. Hang on. Your questions occupied the whole time here, and we're a bit ahead of myself. Let me return to the talk proper. It is an abstract, and that abstraction contains both the operation set and a canonical abstract microarchitecture. The concrete is created from that abstract by a set of specifications, and those are particular examples. Why do it that way? Because creating a CPU by hand is fabulously expensive. Furthermore, the work to do it is incredibly dull, error-prone, tedious, wasteful. And because it is so tedious and wasteful, the final design is often very suboptimal because people were so sick of it they didn't want to do it anymore. We knew that we were going to need to implement and re-implement as a new machine under development. We didn't have already existing chips we could just steal hardware pieces out of. So we didn't want to do a moving target from scratch. Instead, we got the software to do it. The result, with these tools, we can address multiple markets efficiently. If the market situation changes or there's a demand for a new chip, we can produce one very quickly. And that development process, which ultimately has to be paid for by the customer, whether they do it as NRE or as in margin and final sales, makes it being economical for both us and the final customer. We are a business. This is not a charitable open source operation. Our goal is to be a commercial product. So, taking a particular chip, such as Crimson, that's a 2-core chip, and furthermore, the 2 cores are not the same. It's got a copper core and a silver core in it. Mixed core structures are not all that common. Think of the Sony Cell, which had eight of their funny cores and 1 PowerPC. Exploding that up, the copper core. Internal to the copper core, there's still more nested components. There's special registers, stack pointer, program counter, things like that. There's caches, there's ALUs, there's individual components. And the way we are specifying the architecture of a family member as opposed to the instruction set. You saw in addition to the instruction set, but to specify the architecture where we added the floating point unit, those are specified by recursive specification. We start at a board level, list all the components that are at the board level, take each one of those and say, well, what components are inside that? Take each one of those and determine what ones are inside that, and so forth. And yes, it's components all the way down. Apologies to Aldous Huxley. Each one of the components at every level have numeric parameters which help to define their function. A component, which is the belt, One of its parameters is how big is it? How many different positions are there? That's simply a number, a constant in that specification file. I'll be happy to walk you through that specification file in detail and show you what each one of the things are. Caches have got more arguments. How many banks? What is the line width? Eviction policy? Lots of other arguments as well. The predictor table sizes. Components that are of the same kind but have got different values can be created and put in palettes. And then when you're actually creating a member, you pull individual ones off a preset palette, or if necessary, make a new component with a new set of arguments. Behind the components, each one of those has handwritten software. The sim has to be able to emulate whatever it does. And that handwritten code defines what this component will do in hardware in the machine. It produces the emitted Verilog. And the emulation function in the sim is definitive. If the hardware and the sim differ, the sim is right, no matter how loud they scream. Clock domains. The hierarchy of definition does not correspond to a physical layout. In fact, the hierarchy of components crosses boundaries. A board is not the same as a chip, is not the same as a core on a chip. But within any one of these levels, hardware requires clocks. And different components in the physical device get driven at different clock rates. So our sim emulates the clock distribution and the clock values at picosecond accuracy. And part of the specification is to say this component and this component and this component and this component all share a clock. By default, subcomponents in the tree of components inherit the clock domain of their parent, but they can be hooked to anything, and that's part of the specification, is to hook them together. There's crystal components, which are what drives those clock domains. This is down at what real hardware really does. PLL, phase lock loops, connect clocks by changing the rates. And the ratio registers to change the rates are in MMIO space, so they're reachable by a running program. And this one, many people seem to find somewhat mind-boggling, because the sim is simulating at picosecond, not cycle accuracy. And it is modeling the clock distribution and the changes in the clock rate. A running program in simulation, that is a running simulated program, can change the clock constants of the simulated hardware that it is simulated to be running on, and changing the simulated clock rate that in the simulator it is executing at. Okay? I see some nodding heads and other people are going, blah, blah, blah. No matter. The memory hierarchy is similarly created by hooking things together. The whole structure makes use of the notion of a request stream and a response stream, and each component in the hierarchy can be hooked to any other component, is all done with streaming. The sim and the hardware uses predictive throttling, so there's no handshaking is required, and so everything runs at full speed. And we're now at the belt. Nearly everybody held up your hand. Everybody know or remember or willing to take a chance on what the belt is and how it works? Yeah? Okay, so let me skip this and we'll go directly into the code. Back to the test case. And we have to make it, so testasm.sim. This is the same thing we did the first time, way back at the very beginning, and we failed on the floating point. We now, having added a floating point unit, that we should not fail. And indeed we didn't. The build produces, quote, useful, end quote, statistics about the program, which, because this is such a trivial program, the statistics are not very useful. But if you got bigger programs, the statistics are showing what gets encoded where is useful. And so that's what that funny thing is about. And now we need to actually run this thing. We're now going to run the sim. And build/test.sim. Okay, the simulator interface, the user interface, is designed to look as much like GDB as we could make it. So nearly all of the commands will be familiar if you're familiar with GDB. It starts up by giving you a little bit of background information. These are all defaults. We're running this core in that chip on that board. And we picked up that information by default because it was information that the tin test case had been using before, and because we didn't change it, we're still using that chip and board. And as is typical, we're starting up. Remember, this is a bare, cold machine. You have just had the power come up. There's no BIOS. There's no runtime system. There's no operating system. This is a sim of real hardware. And when real hardware comes up, you come up in the default clock rate of what the crystal actually is, of which 50 megahertz is typical. Later on, in the course of coming up, you'll raise that rate using that PLL and the clock domains. But that is our assumed clock rate. And we're only simming that much because memory because we don't need any more for the purposes of these tests. Here is our con operation. Can you am I blocking anybody? Can you see? This is our con operation. And it was the first operation of our little program. Now, in order to see the effect of this, we need to be able to show you the values on the belt. And the command to do that is display. If you're used to GDB, it's a display because we're going to have it automatically display the belt contents every cycle, /W, display /W, space, $belt. Okay. And now when you type S for single step, that is the current contents of our belt. For free, the hardware coming up gives you I twisted around here. The hardware coming up gives you a starting pair of zeros for argc and argv. You're not actually being called from anywhere. You're being called from the power up sequence, but you get these two values to start on your belt. And these are the two constants which we had put up there, one being that first instruction and one being the second con here. Constants occur in reader phase, and this belt display occurs at op phase, so anything in reader phase has already happened. Those of you who have been through our phase talk about phasing, everything that has been in reader phase has already happened before the UI got control and displayed the belt. So if I had a con and an add in the same instruction, and I was looking at the belt, it would show the result of the con, but not yet the result of the add. We have to pick a point to show as things run through the phases, and that's where we pick it. The display is as of the start of op phase. In any case, those are our two floating point constants. And if you now do an S, this is our add B, and S again, or just return. The add is now in the process of happening again, and there is our result. The sim is telling us This corresponds to belt position numbers. The numbers here are telling you which instruction number it was that produced this value, that added it onto the belt. So this says that this add B was produced by the add operation, which was in 3, which was there. Okay? So from this information, you can look at a belt value and say, who was it that produced it and who dropped it onto the belt? Yes?
What about the metadata, like if a NAR was produced?
You'll see that very shortly.
Oh.
Okay? In the absence of any other information here, there is no metadata except for width. And width, because of their /W when we ask for the display, the width is being shown by the number of zeros. Okay? So, and we now have got a value, and that's all this little program did. We did a floating point add. Drop out of that. Q, okay. Now we need to edit the test case because we have a pepper in the wings. SRC. I am very much in your way, aren't I? Does that help?
Here we go, okay.
Okay, now we want to switch the commented out parts. So remove the / up here and there. So those will comment out. And add a / in front of the / and another one down at the bottom. So we're commenting out the comment. Okay, I think we're right. And all the new ops need to be peppers.
Okay.
Where does that return return? Where does the return command return? If it's a
The return here at the bottom?
yeah.
That is a final operation here, and if we'd actually executed through it, the simulated hardware would have detected stack underflow, would have attempted to assert a hardware trap, would have discovered that the trap vector was not initialized, and we got a while address off that, would attempt to do another hardware trap. That in turn would wind up into a system hardware trap, and at that point it will simply bail out and say, and power down the machine. Okay? Yes, we do simulate all of that. I have not bothered showing it to you.
So put on that and make it.
Or does this make any sense? Yeah, I think it does. Yes, so make it.
So this is a new program that you're going to now recompile into a new sim?
This is we will now be making a new sim. Each time you go to sim a program, you've got a new sim that only does that program.
Okay.
This is why it takes a little while to do that, because and longer if it was a bigger program, but it saves total simulation time substantially doing it this way. It is, however, not the instant gratification turnaround that many programmers have come to expect. Okay, and now we'll run it. And a display /W. And an S. Okay. Now, what our code is doing, we've got a constant value 7 and a constant value 5, and we're going to apply the pepper op to 7 and 5. Those are our two constants, 7 and 5, on the belt. Step 1, There's our pepper, and there's the result of our pepper operation. And you can figure out whether those bits are right yourself offline. Okay? Now, this pepper operation, where were we? Up there, was the default ignore overflow and do signed and unsigned because they're the same. Now, if we could now go to the next test, we've got a nice big number down here, and we do a pepper UX. U is unsigned, and X is treated as an error in the case of an overflow. So now, someone asked, what do you get about the metadata? Well, that's what you get for metadata. We detected the fact that we had an overflow condition, and we dropped an integer overflow nar on the belt. Okay? Down to the next case. We will overflow this one too. This is the saturating one. Go down, see that's unsigned saturating. And guess what? There's our saturated value. And again, pepper UW, as you see, the result is wider. One last case. You're seeing scalar arithmetic here. But how about vectors? Well, you got ahead of me here, right? Hang on here for a moment. That constant up there was a con of 5, and the splat operation is replicate a scalar into across a vector. So that 5 got splat. Can we hold it still for a moment?
Right, there you go.
That constant 5 got splatted into this vector of 5s. Okay? The read operation is actually this is a read from what's called a popular constant, or popcon. And the particular popcon, which is that one, is the iota popcon, and it returns 0, 1, 2, 3, 4, or as many elements as is required. Standard iota, except that it's coming out as a constant rather than than being an operation. So that's where that value came in. And so now we've got two vectors on the top of the stack, one which is all 5s and one which is a increasing sequence. If we now do pepper of B0, B1.
What's that note operation?
What?
The NOPE. Middle of the screen.
That's a no-op.
What kind though? It's special.
What?
Well, what's the E for?
It's an XU side no-op. Remember, we got two sides. There's an op E and op F.
Okay.
And here is our vector result. And if you figure out what a pepper does, sure enough, you'll discover that pairwise, if you apply a pepper to each of those pairwise in the vector, there you have a vector of peppers. Madam, I must thank you. Your cat has a wonderful name for this talk.
And he will be honored.
Okay? You're seeing a real sim, a real tool, one we've been using for years, and how we use it. Now, how are we doing for time?
I think we should.
Okay, I'm certainly going to skip across all of the belt stuff and see. Let me get down to a summary and a few final words. I'll skip the MMIO unless people have questions. This deserves comment. There are other vendors who do specification construction of chips in one way or another. However, their approach is fundamentally different in ours because it has got different purposes. Typically, these are being used to add special purpose embedded operations to an already existing single core. And they hook into the new operations hook into a bus structure that is dedicated exactly for that purpose. And they are encoded using previously dedicated bit patterns. That's not our purpose. We're not trying to add custom operations. You've seen an example where we can, and we could, and if waived a sufficient amount of money at us, we'd even do it for a customer, but that's not our purpose. We're attempting to produce optimal subsets for particular family members. The encoding is different. They use reserved bit patterns, manually selected. Ours is automatically generated. The specification process is a one-at-a-time manual process, and it's a pattern-based system for us. So while we certainly did not invent the notion of a specification-driven architecture, both the goals and the way it's done is substantially different. In sum, everything is done by composing attributes, and the tools that are produced use the cross product of those attributes. The architecture is done by recursive composition, mix and match, and there's a compact notation for doing it all in. This talk will eventually, after post-processing, and it's going to have a good deal more post-processing even than our other talks do, I can tell. Will eventually wind up on our website, and you'll find it there at that URL. If you're interested in announcements or technical material, that mailing list is the thing to sign up on. As we are able to produce white papers, talks, and what have you, they get announced on that mailing list. And that's it. It's nice to be able to talk about the software as opposed to the hardware and the architecture, because I'm a software guy, and a large amount of that is my code. Questions?
So at the beginning, you kind of showed how you're using C++ as the assembly language.
Again?
At the beginning, you used C++ as the assembly language in your example. Can you talk about how you would imagine that working for just-in-time compilers? You're not going to invoke C++.
Yes, I can. The problem is not the assembly language, because your JIT probably would not want to produce source assembler, overheads of various reasons. So the fact that when you're coming in from source, you're coming in from C++ is sort of irrelevant to a JIT. The big choice for a JIT is whether you want to have the JIT be written once for all members and produce abstract MIL, or be already specific to a particular family member and produce code precisely for that family member. While certainly somebody could do the latter approach and have a specific JIT for a specific target, in general we will discourage that approach. We want the JITs to, as indeed our own tools, to produce the abstract form and to use our specialized library, which turns that abstract form into properly scheduled, because basically we're going to do a whole lot better job of scheduling than any JIT is ever going to want to put the work into doing. This seems to be the right way to do it. Yes.
General purpose question. Comparing with general purpose machine, you get 10 to 1. If you try to simulate for a specific purpose machine comparison, should you get equals? You don't get any performance. What I mean that if you try to make a DSP out of this, would that performance improvement work.
Okay, hold on. I'm going to have to get somebody to repeat it.
You've compared it to a general purpose machine. What types of comparisons do you get, say, to a DSP?
The mill will make a fairly good DSP, but it contains within itself a whole lot of things that are redundant for typical DSP work. For example, we put a lot of work into branch prediction, and most DSPs don't need it. We do a lot of work into, not shown even on talks that we've done yet, but coming up, a lot of work into things like access, multi-threaded access, into inter-process security and inter-process communication, things which DSPs essentially don't care about. Yes, we will be a pretty good DSP, but a specialized DSP which fits the application will probably do better than ours. On the other hand, if you're all worried about the future and you're expecting your application to evolve, which is typically the case even for embedded work, you'd be a lot better off with us because you would not have to just completely rethink and rewrite your program to go to a whole new chip with a whole new architecture, whereas ours, you simply move up the family to get more capability if you need it. We are fundamentally designed to be a general purpose chip, but we've got enough of a power and performance advantage that we're suitable for a whole lot. But the kinds of things that we're not good at, if you could use a GPU for your application, use a GPU. We're not right. Similarly, if you're extremely low level, the mill has to be a 64-bit chip, and if your application is running in a thermostat, well, go buy a Z80. It does a real good job, we're intended to be from the low, middle to way past the high end of general purpose. Yes.
Yeah, so
This gentleman here in front was first, I think.
In the context of computing, you're talking about eliminating entropy. Now, as a thermodynamic concept, I know what entropy is, but I wonder, is that something that you could clarify?
Okay, this is a standard term. This is a standard term in encoding theory. One measures the density of an encoding in terms of its entropy. Comes from Shannon and used very widely for measuring the merit of communication protocols, which of course an instruction encoding is a communication protocol. And essentially, it's a measure of how much waste is there in the encoding. How many other things could you put in the encoding without having redundancies? And it's just a standard term for that measure. The goal is to minimize entropy. You want your code you minimize wasted entropy. You want your code to have a maximal entropy, and the algorithms used internally attempt to achieve that.
Okay. Thank you.
And now.
Okay, you were talking about that to speak up. You're saying that for things you want to use GPU for, use a GPU, but I've looked at different crypto algorithms, and yeah, you can use a GPU for a certain algorithm, but it's only going to be 5 times faster than a CPU because of all the branching it does. And the branching it does is because it wants to be more secure against the GPU attacks. So
Repeat.
For encryption.
I'm sorry, I'm slightly deaf.
For encryption algorithms,
Yeah?
A GPU may only be 5 times faster because of all the branching. So
Yes. Well, the sort of the defining difference between general purpose codes and special purpose or DSP-like codes is it branch heavy. GP code is branch heavy all over everywhere, and the mill is designed to deal well with that. If you have something that is, in market terms, is embedded, but in programming terms is branch heavy, then yes, a mill would do very well, thank you. Branch heavy, flow of control heavy, calls, task switches, all of those things. I mean, a task switch for us is like 4 cycles, the whole thing. Go on, more?
That's a follow-up question. I want to ask about DSP in this. My actual question was, with all of the tools you have done and optimization and being able to define new instructions, forgetting about the jump and everything else, would that level of capability in your design to be able to define instruction for a specific purpose problem, would that compare to creating a specific purpose hardware resistance?
This is, if I understood your question, I think I got it. This is primarily a business question rather than a technical question. We see ourselves as a vendor of general purpose chips. On the other hand, we're a startup and we're not turning down money. Consequently, if there were demand for special purpose things, yes, we'd do it. We would, however, pretty much require that the special purpose be able to express at however expensive cost in regular operations, so that when that special purpose operation hits a specializer for a different chip that hasn't got it, we've got emulation code that we can drop in instead. We really don't see the value in having code that only runs on some members. We want all codes to run on all members, but though not necessarily equally fast. Now, there's an exception to this. There's sometimes that you have big hardware blocks. A crypto box is an example, where it doesn't fit into an operation model anyway because it takes too long. And this thing is best modeled essentially as an I/O device. And we do have interfaces, not shown here, but we do have a whole set of interfaces, which are components that you can plug into your configuration, that essentially lets you plug in on-chip I/O devices, but they feel like I/O devices in terms of the way the program interacts with them. And those, the embedded world in particular, the cores are a tiny portion of the amount of work that goes into a chip. If you're doing a router chip or something like that, this proprietary IP all around the thing, with a core here and a core here, but that's not where the value added is. They can use an ARM core or a mill core or whatever. The value added is all the proprietary stuff around the outside. And they're not going to want to show that to us, and that's fine. We don't want to do it. We will wind up vending hard macros into the people who have got all the proprietary stuff and plop, 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 and sure, here's your chip. But we do have in this the flexibility that we can hook to their stuff in a convenient way.
Isn't the pepper instruction a counterexample to run on all members?
We notice that we have not specified what the emulation equivalent of this is, although I think you could probably write one pretty quickly.
But you wouldn't do that.
Oh, of course we would if we were going to release a chip with a pepper on it.
Really?
Oh, yeah.
So it's to a single, unique customer who
if the customer told us that he considered the operation to be proprietary and would not let us use it, we might still, with sufficient green, be willing to do the job for him, in which case it's his, but it's his problem, and it won't run on anything else. Okay. But the basic model is if he's got something that actually would speed up his problem enough that it's worth doing, somebody else is going to have the same problem, and we'll put it in the core machine. It may not appear on every member. It may not even appear on any member except his, but it will be in the architecture. Yes?
You didn't say anything about test vector generation. Are you going to like automatically generate test vectors for the pepper instructions so that you can test these chips on, on the test head?
You bet.
Okay.
The test vectors are heavily domain determined. Thus, for example, if it's a half word and it's untimed integer, you know what the bit patterns are that the vector is going to use when it's generating tests. And it'll just run the changes of all the attributes and all the values and all in the slots that it's in and what have you, and just crank out code. And you, I believe, mentioned dinner.
Yes, Amici's, Castro Street. Before they close at 10.
Quick question. So if you're minimizing entropy, does it mean that you cannot have an illegal instruction interrupt?
Again?
If you're minimizing entropy,
Yeah.
does it mean that you cannot have an illegal instruction interrupt?
Oh, no. Well, you can have illegal unmeaningless combinations.
Okay.
But fundamentally, no, we do our best to not have any illegal instructions. Yes, certain combinations are simply not meaningful. But an example, for example, is a widening operation, which you can double the width of something, but you only double the width up to the maximum size. And so if somebody has a maximum size value and he attempts to apply the widening operation, you'll get a fault.
I have plenty more instruction encoding questions to ask.
Hmm?
I figure we should get to dinner before I ask all of my questions.
Fair enough.
But I do think it was T.H. Huxley, not Aldous Huxley.
Hmm?
Turtles all the way down.
Yes, it's turtles all the way down. It's
T.H.
Huxley.
Thomas Huxley, though, not.
Yes, I think so.
biologist.
It's easy to mix up your
You are
Huxleys.
tall.